Hello all, I'm excited once again to welcome you back to our lectures. Emeka Udenze is speaking. This is the second part of the GOB series, and it's very important we start with the review of critical topics that you did in the last part of this class. Now, building foundations on those review and trying to reenact them will be a centerpiece for proper understanding in this particular class. Without much ado, we're going to take it off from there immediately. Again, if you're used to my class, you know what I usually do. I usually start with a quote. In this case, I'm starting with a quote from a chemist. He said, "We define organic chemistry," which is what we're doing. This is an organic chemistry class, and biochemistry. He said, "We define organic chemistry as the chemistry of carbon compounds." That's basically, it was from Augustine Kekule 1861 that gave us the best definition of organic chemistry. Of course, we have an exception, which we're going to talk about much later by the time we dabble into that. And you see, I put a caveat here. It says challenges ahead. Now, this class is a busy class with a lot of concept and a lot of materials to cover. But I want to tell you this. We're going to do it together. We're going to swim through this together. We're going to go through this together. And at the end of the day, you're going to come out in flying colors. Let's take it off from there immediately. Now, there are 3 learning goals I want us to achieve here. It's a little bit more, but I try to break them down into 2 opposite pieces. The covalent bonds, which will be the centerpiece of the structure of organic molecules. But we're also going to brush out a little bit of what ionic bonds are. Then we'll look at drawing Lewis structure. Lewis structure simply means the molecular structure of compound. Remember, in the last part of this class, we talked about Lewis structure, but now we're going to be changing that word a little bit from Lewis structure to what we call molecular structure, or we say structural formula, molecular structure, or we say structural formula, or even structural formula. That's the word you see me use more or less. And then finally, we're going to see what is the condensed versus the expanded structure, where we can write formulas in shortcut, and then we can also write it in the normal expanded version, showing all atoms completely and the bonds. All right, let us take it off from there immediately. Now, what is a covalent bond? Just to remind you, a covalent bond is a type of bond that is formed when atoms share electrons between one another to achieve octet rule. Remember this, the main objective for any type of bond, whether covalent or ionic bond, is for the individual atoms, because atoms usually don't exist as individual atoms in real nature. They always want to be bound with one another, go into relationship to achieve octet rule. So the reason why atoms actually go into relationship is that every atom wants to achieve the octet. And of course, remember what the octet is. Octet is the ability of atoms to have what? 8 electrons. They want to have 8 electrons in their outermost or valence shell. And that is the only way they become stable with one another. In that process, the atoms become electrically neutral. Because the way we draw atoms in single atoms usually is not how they exist. Now, of course, covalent bonds are formed between, it's important we say that, it's formed either between a non-metal and a non-metal, or a non-metal and a metalloid. So this is how you form it. If it is between a metal and a non-metal, we're going to be talking about ionic bond, but we're not coming there. In ionic bond involves just the transfer of electrons. Here we're going to be seeing, I'm going to try to show you a demonstration to show you how atoms share these electrons to make sure they achieve the octet rule. I'm going to be using a common culprit here. I'm going to do hydrogen and carbon. First of all, let's look at, I have a periodic table in the next page. You see, hydrogen is in group 1. What it tells, how do we determine the number of electrons in an atom? It's just to look at the periodic table and see the group in which it belongs. Hydrogen is in group 1, therefore it will have 1 electron in its atmosphere shell. What about carbon? Carbon itself is what? In group 4. Look at it, group 14 or group IV. Remember, in American system, we still use the Roman numeral, the older system that uses Roman numeral. So this is group 4. Now, that is where, so it has 4 electrons. So hydrogen will have 1 electron in the atmosphere. This will have 4 electrons in its atmosphere. What it means is that hydrogen forms the duplet. It wants to look like the helium. So it only gains 1 electron to do that. Whereas carbon will have to gain 1, 2, 3, 4 electrons to look like the neon. Now, let's see what happens. Let's go back to what we have there. So I'm going to try to tell you. So having told you what hydrogen and this. Now we know that hydrogen is a group, has 1 electron. So what happens? Now let's see how hydrogen combines plus carbon. Let's see how hydrogen combines with carbon. So we're going to start by drawing the Lewis symbols of each of them. I'm going to try to draw the Lewis symbols in a neutral form. What's the Lewis symbol of hydrogen? The Lewis symbol of hydrogen is, remember, here hydrogen has, let's see, it has 1 proton and 1 electron. Here carbon has 4 protons. No, not 4 protons. Let's do the total. Not in the utmost shell now. Let's just total. We know it has 4, but total it has here is 6. Is carbon is number 6 element. Carbon is number 6. So it has 6 proton and 6 electron. Now, in Lewis symbol, we're still going to brush this in the next page. In Lewis symbol, you write the Lewis symbol by showing only the number of electrons in the atomos shell of that atom. Hydrogen is in group 1. So if you want to show the number of atoms in each atomos shell, I'm going to say 1 dot. Although this is the only electron it has. What about carbon? Carbon has 4 electrons because it has 2 inside, which is the core electrons. Remember, the core electrons does not go into bonding. It's only the valence electron. Now, carbon has 4 atoms. So we're going to have a representation of 4 dots, which is 4 electrons around it. Okay. Yeah, I'm going to try to give myself some space around here to put that. So, and then I said it has 6 protons and 6 electrons. So they were much more interested in the number of electrons it has. Now, if both of these guys combine together, their basic objective is to achieve the octet or the duplet. Hydrogen achieves the duplet because it only can get 2 electrons to look at the helium. So remember, hydrogen is always an exception in the periodic table, so it's odd. But we know, so hydrogen is only going to get 1 electron to form 1 bond, of course. Whereas carbon is going to get 4 electrons to form 4 bonds to achieve octet. So let's see what happens. Now, when both of them have to involve, now because carbon has to form 4 bonds, we're going to have 4 hydrogens here. So we're going to have 4 hydrogens. So what is going to happen? Let's now draw it. So when both of them form, a good example of a compound we'll talk about more, methane. What happens? Let me first of all put these electrons. Remember, these are the electrons that are holistically owned by carbon. Now, 4 hydrogen atoms will come in, and each of them will share 1 electron with one side of the carbon. Look at what's happening here. Now, each of them will come in. One will share this one with carbon. Another one will share another one with carbon. Another one will share another one with carbon. Another one will share another one with carbon. Look at what is happening here now. So I'm not going to complete my hydrogen. So if my hydrogen is here, my hydrogen is here, my hydrogen is here, my hydrogen is here. Now look at what's happened. Each of these hydrogen wants to just be 2. What it means is that it has shared just 1 electron on one side with carbon. So the total number of electrons it has completely now is 2 electrons. That is what it wants to be, to become neutral, to looking like helium. Again, this is 2 electrons because it's sharing 1 of carbon on its own. This is 2 electrons. This is 2 electrons. What about carbon? How many electrons does carbon now have in its atom shell? Initially it has 4, and it is sharing 4 from 4 different atoms of hydrogen. What does it now? It now have 2, 4, 6, 8. It now have 8. So carbon has, in this molecule, carbon has 8 electrons, achieving, remember, our octet rule. So if I redraw this now, you find out that these 2 electrons that are shared between hydrogen and carbon is actually what we call a covalent bond. So if you redraw this, the way we actually draw them, you're going to get this. So a pair of electrons represent 1 bond. This is 2 electrons. A pair of electrons or 2 electrons represent 1 covalent bond. And this is exactly what happens when covalent bond. And this molecule, this methane molecule, is actually what you're going to see that is very, very stable. Very, very stable. And this can exist naturally. Good. So this is how a covalent bond is formed. Like I said again, it's a type of interaction whereby atoms share electrons to form bonds. And this type of bonds are called covalent bonds. What about ionic bonds? Ionic bonds, on the other hand, must be formed between a metal and a non-metal. That is what must happen in this case. So here I'm going to use the usual culprit. Sodium, I'm going to do this with sodium. Sodium and chlorine is what I'm going to use in this case. So I'm going to be using sodium plus chlorine to show you the sodium and chlorine. Now, what group does sodium belong? We go back again. Sodium is in group 1. It will have 1 electron. So it's going to only have 1 dot at its Lewis symbol. So I'm going to have only 1 dot at this point. Chlorine, again, is in group 7. Look at it now. Group 7, IV. They're going to have what? 7 electrons in the outermost shell. All those guys. So let's go back. So it's going to have, so what am I going to do? I'm going to try to distribute it well and leave one side not filled. So it has 7 electrons in outermost shell. Okay, that of this thing, I'm going to redo it. Okay, well, let me use this. I'm going to use a green color because that's the electron that will be donated. Good. Now, I think I should give some space around that. Let's see. So this is sodium and then this is dot. Good. Now, so in each neutral atom, let's see what happens here. Sodium is number 11 in the periodic table. So it has 11 protons and 11 electrons. It has 11 protons, 11 electrons. Remember, one of those electrons is in the outermost shell, which it's going to use them. But remember again, bonding only uses electrons in the outermost shell of the atom. Now let's go back to this. If you go back to this, chlorine is number 17. So you have 17 protons and 17 electrons. That's what it has. Now what is going to happen? We said in this type of bonding there is transfer of electron, whereby the metal loses electron and gives it to the non-metal or metalloid to form an ionic bond. And those ionic bonds usually form as a result of charge. So here we didn't talk about charges. But when this transfer is done, each of these ions that are formed become charged. The attraction between those charges is what we refer to ionic bond. Now what is happening here now? This sodium is going to lose this electron and come and give it to this. What happens? As it does that, it becomes what? Sodium. Chlorine now gets extra 1 to have 8 electrons in its outermost shell. Whereas sodium itself is now going to be what? Sodium is only now going to be left with what? 10 electrons. And the last 8 of those electrons in the ionic compound will now be in the outermost shell to form the ion. So what's happening? Okay, let's see. I'm going to show you something to make it easy. Carbon has 2 electrons in its outermost shell. No, sodium. Then has another 8 in the middle shell. And in the outermost shell, it has 1. It is this one that is going to be lost. Then what about chlorine? Chlorine has 2 in the innermost. In the middle shell, it has 8. And in the outermost shell, it has 7. It is this one will go into bonding. These ones are the ones that will go into bonding. So let's see what happens. Now, when both of them form ionic bond, look at what's happening. Carbon is going to lose this one. And the moment it loses this 1 electron, look at what happens there. It doesn't have anything remaining. But however, it now assumes a charge. Whereas chlorine itself, now remember, chlorine initially has 1, 2, 3, 4, 5, 6, 7. If we receive 1 from carbon here, what happens here? It now has extra 1. That's what happens there. It now has extra 1. Now, it has 8 electrons in its outermost shell, and it now assumes a negative sign. Now, now see what happens here. The attraction, remember we said unlike terms attract. Unlike terms, the attraction between these positive and negative ions is what we call an ionic bond. And that particular bonding is much more stronger than what you have in the covalent bond. And that is why ionic compounds usually do what? Have higher boiling and melting point than covalent compounds. So look at what is going to happen here. Remember what we said earlier. Now, this one has lost 1 electron. Nothing happens to the proton. It is only the electron. What it means is now, it's only left with how many electrons now? It's only left with 10 electrons. Whereas this one gained extra 1, it now has 18 electrons. So what does that tell us about the electronic configuration? Remember, if he loses this one, it's now going to be 2, 8. Yeah, that means 2 plus 8 gives you 10 electrons because it has lost this one in the outermost shell. What about this one? This one used to be 2, 8, 8. If you add this one to this place, it becomes 2, 8, 8. It now has 18 electrons in the outermost shell. Now, these entities that are formed, that are charged, are what we call ions. And the attraction of these ions form the covalent bond. We don't represent them as dash, as lines as we do here. We just leave them the way they are because we know there's an attraction, there's a pull between these 2 ions. So, formation of this type of bond leads to what? Ionic compound. Ionic compound. And sodium chloride is a good example. So these ions attract each other. Now, how do we even know that this charge has been formed? How can you actually quantify that this charge? Look at what is happening here. Remember, initially, this one has what? Excess of electron, right? It still has 11 protons. 11 protons, you say 11 minus 10 is going to give you 11 minus 10 electrons that it lost will give you 1 plus. That is why it now has, it's no more charged. Whereas this one is going to be 17 minus 18. Remember, it has 17 here. If you say 17 minus 18, it's going to give you -1. That is why it now has those charges to form bond between themselves. So this is how we form covalent and ionic bond. Let's take it off from there immediately. So now what are we going to do here? What you said we're going to try to know how to write the Lewis symbol of this element and use that to predict the number of bonds. How do we do that? It's simple. Now, since we're talking about covalent compounds, we're not going to even talk about ionic elements. We're going to talk about those non-metals alone plus hydrogen. Now, an atom forms a bond, forms the number of bonds that is equal to the group number of that element. No, 8 minus the group number. 8 is the octet minus the group number. Or there's another way we can say that the non-metals form the number of bonds that's equal to the number of electrons they will gain to form the octet rule. So what number of electrons would each of these ones gain to form the octet rule? How do we do that? We're going to see the group in which it belongs. So we determine the number of electrons in the atmosphere, write the symbol, and now know how much electrons it's going to gain. Or we can use this formula to say the number. So let's start. Carbon is in group 4. We already did this. Group 4 means it has 4 electrons in the atomos shell. And how many electrons do we need to make this 8? We need 4 electrons. So 8 minus 4 will give you 4. So carbon forms 4 bonds. And those 4 bonds can be in double or single or triple. Forms 4 bonds. Oxygen is in group 6. If it's in group 6, what am I going to do? In group 6, we have 6 electrons. This group 6, they have 6 electrons in the atmosphere. So I'm going to have it this way. So it only needs 2 electrons to become 8. That's exactly what it means. No, I gave it too much electrons there. Okay, this is 6. So what that means, I'm going to say 8 minus 6 will give me 2. So oxygen only forms 2 bonds. Now, the importance of this is that we're going to be using this idea to predict the number of bonds that each of these atoms will form. So that when we see them in a molecule, we don't have to necessarily count the number of electrons to draw the Lewis structure or the molecular structure. Nitrogen is in group 5. This is group 5, Va. What it means is that they will have 5 electrons in the atomos shell. We use dot to show that. So you put 1 here. So if you say 8 minus 5, it's going to form 3. It can only form nitrogen can only form 3 bonds and 1 love pair. What about sulfur? Sulfur is in group 6 like oxygen. Sulfur is in group 6. So sulfur 8 minus 6 will still form 2 bonds. And we're going to say, we're going to do it this way. 2, 4, 2, 4, 5. Put another one here to be 6. What about chlorine? Chlorine is in group 7. All group 7 elements to have 7 electrons in the atomos shell. So let's try to situate that. So these 7 electrons. So what that tells us is that it's going to gain what? 1 electron. They will just gain only 1 electron. Because 8 minus 7 is 1. And therefore they will form only 1 covalent bond. And what about hydrogen? Hydrogen wants to look like helium, which is 2 because it has only 1 electron. So what hydrogen will do is that it will only gain 1 electron. Hydrogen is it will gain 1 electron to become 2. So hydrogen only forms 1 bond. So with this idea of knowing the number of bonds each atom will form, you can easily draw the Lewis structure without having to resort to what we did last in the last class by counting the electrons. But I'm going to show you how that is done using those 2 ways. It says draw the Lewis structure for the following. Now let's draw the Lewis structure for. I'm going to do it the usual way you did, and then the rest I'm going to be doing it with the new thoughts I came up with. So I'm going to show you that. Now, here, carbon, you know the first thing you do is to calculate the number of electrons in the atomos shell in that compound by knowing the number of electrons in each of these atoms. Carbon is in group 4. I talked about earlier. That was the example I used in forming covalent bond. It has 4 electrons plus. Hydrogen is what? Is in group. Hydrogen, okay, that I don't want it to stick together. Okay. Hydrogen is in group 1. It has 1 electron, but it has 4 atoms. 4 times 1. So the total number of electrons here is 8 electrons. So what do? Now, you determine the central atom. Remember, carbon is always the central atom whenever you see it in a compound. It's always the central atom. Hydrogen cannot be central atom because it can only share just a pair of electrons. It can form one bond. So if you put this, you now use bonds to distribute the number of atoms at the periphery. If you look at this now, remember we said each covalent bond is 2 electrons. So this means 2, 4, 6, 8. We've used all the electrons, and this is the Lewis structure of atom. And that makes sense. Carbon forms 4 bonds. That's already what we established. Now, let's use that thing I said to do the second one, hydrocyanic acid. In hydrocyanic acid, remember, here, hydrogen is 1 plus, carbon is 4 plus. Nitrogen is in group 5. You can check that. It's in group 5. So it's going to have 5 electrons in its atomic shell. So it's 5. If you add all this, it's going to give you 10 electrons. Now, let's see what happens. Carbon is always at the center. And I wrote it that way for you to see. So you're going to say carbon is at the center. And then you're going to add your nitrogen and your hydrogen. Now, I'm not going to use the counting of electron method to do it. Look at what I'm going to tell you. Hydrogen, where can I just add extra bond here? I can't add anything between hydrogen and carbon because hydrogen only makes 1 bond. You can't do anything there. But nitrogen, what did we say? Let's go back. Nitrogen forms 3 bonds. Carbon forms 4 bonds. So we're going to make sure that we satisfy both of these two guys. Here, carbon has 2 bonds already. So what it means, it needs extra bond. Now, carbon now forms 4 bonds. 1, 2, 3, 4, which makes it correct. What about nitrogen? Nitrogen forms 3 bonds. 1, 2, 3, which is correct to be neutral. So if we have done this, that means we've achieved what we want. So what do you now do? But we're not done because each of them need to satisfy the octet. Remember, that is the magic message. To satisfy, carbon here has satisfied the octet because it has 8 electrons. What will you do to nitrogen to satisfy the octet is by adding a lone pair. So now it has 2, 4, 6, 8 electrons around it. And this is the Lewis structure of hydrocyanic acid. If you want to prove that, let's count the number of electrons to see if it matches this. So this 2, 4, 6, 8, 10. And that is very correct. So this is what I'm going to use to do the rest of these ones as well. So again, let's look at this one. Here, carbon, I'm not going to count the electrons. I'm just going to know that carbon is always at the center. So if I say carbon is at the center, I put 1 oxygen at this point. I put an iodide at this point, iodine. Now, what did I tell you about? Let's start from iodine. What did I tell you about group 7? Group 7 element like chlorine, will form just 1 bond. That means it will have the rest to be a lone pair. So it already has the 1 bond it has. So you don't need any other thing. What you do is to satisfy the octet. So to give you the octet, we're going to use lone pairs. Lone pairs are always dispensable. So if you're going to put lone pairs here, it will form 3 lone pairs. So group 7 element does what? They form 1 bond and 3 lone pairs. That's how you actually know them, to form neutral atoms in the molecule. So this is what it is. Now, but carbon is not. Carbon is 1, 2, 3. Carbon usually doesn't want to have a lot of lone pairs around it. It usually wants to satisfy itself with its bond. So how can you do that? You add extra bond here. If you add extra bond here, carbon is now 2, 4, 6, 8 is satisfied. However, nitrogen is not satisfied, but nitrogen can't form more than 2 bonds. You don't have 2 bonds. What do? You have to satisfy the number of bonds with octet rule. So this is how you draw this molecule. All right, let's do this one too. This is carbon dioxide. I know I taught you how to draw carbon dioxide in the last class, but now we're going to apply some other thing. Again, carbon is at the center. Carbon always forms 4 bonds. Oxygen forms 2 bonds. We need to satisfy that. So to form 2 bonds with nitrogen here, we're going to put this. It forms 2 bonds. Put this. Now carbon has 1, 2, 3, 4 bonds or 8 electrons. But oxygen has 2, which you usually have. But however, oxygen must be satisfied and to be given the what? The lone pairs. That is how you draw this Lewis structure without having to necessarily count the number of electrons. Now let's draw the Lewis structure of these ones. Now for these ones, I'm going to draw the Lewis structure. See, I'm not going to have any recourse to begin to count the electrons at all. I'm going to show you another way of doing this. This is like, some of these things are written in what we call the condensed structural formula. These things are all written in condensed structural formula, or their formula. Okay, not condensed. Let me just say they're written in their normal formula, right? So let's see how that works. Now, you see, whenever you see CH3, CH3 means carbon having 3 hydrogens attached to it, and then it's connected to another. And you remember, carbon is always at the central atom. So let's do that. So what I'm going to do here is to put my carbon here, and then I'm going to surround it. This carbon, this is always at the center. This is what we just have here. Carbon has 3 hydrogens and then connected to chloride. But however, we're not done. Chlorine needs what? Those lone pairs. Remember, is in group 7, it has 1 bond and 3 lone pairs. Very soon after this review, I'm not going to bother with putting lone pairs in atom again. But it's important you see that clearly and understand the reason why we're adding this lone pair is to make sure that this atom satisfies the octet rule. That is how to draw this. Now let's look at this one. In drawing this one, look at what happens here. Again, carbon is always at the center. Hydrogen can never be at the center. In organic chemistry, most of the elements we'll be looking at will have a lot of carbon to themselves. So always know that those carbons will form those bonds with themselves before they're being even connected to any other stuff. So we're going to have 2 carbons to be at the center here. There are 4 hydrogens. We can add those hydrogens. If we add it here, we're not going to have anything we'll add this side. So we're going to add those hydrogens here and here. Add it at the outside. Hydrogen forms 1 bond. We're already satisfied. But carbon is not complete. You're not going to put, if you put a lone pair here and put a lone pair here, you're going to be forming a lot of bonds, which will be very confusing. In fact, if you count it, your bond is going to exceed your lone pairs. What do? It forms 4 bonds. Always make sure carbon forms each 4 bonds with a bond before thinking of lone pair, which exactly what carbon does. Carbon wants those bonds. It doesn't want the lone pair. It doesn't. In fact, in this class, we don't have to get into any problem that will result to carbon forming charges or getting a lone pair. Most times, it's going to be neutral, forming all 4 bonds. So if you look at this one, has 4 bonds. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. And this octet rule is satisfied. Let's go to this one. This one now, the same thing. Here, there are 3 carbon atoms. So anytime you see more carbon atoms, attach all the carbon to themselves first. And then we go to hydrogen. I'm going to attach some hydrogen here. We have 6 hydrogen and see if we have it completely. Now, I'm going to attach some here. Now, okay, let's see. If we attach all the hydrogens here, remember, we have 6 hydrogens, right? Now, this one, 1, 2, 3, 4. Here, there's 4 carbon. Here, this one is not satisfied. What are we going to do? Okay, now we don't have hydrogens anymore. So what are we going to do? We're going to add a double bond here. If you add a double bond here, what does that tell you? This now becomes 1, 2, 3, 4, 5. Carbon cannot have that. What do? I'll clean it. We're going to clean this. This is wrong. This is what it's going to be. And then where do you now add that hydrogen? Look at what happens. Here, carbon is forming 1, 2, 1, 2, 3, 4 bonds. It's okay. Here it forms 1, 2, 3 bonds. To add hydrogen, if you add another bond here, this carbon here will be too much bonds again. So therefore, we're going to use that hydrogen and add it at this point. So now we have 1, 2, 3, 4, 5, 6 hydrogens. 1, 2, 3, 4, 5, 6 hydrogens. We have 1, 2, 3 carbons. And all these carbons satisfy their own octet rule. So this is how we draw this Lewis structure. Now let's look at water. Water is a popular culprit to usually draw the Lewis structure. Look at what we do. Hydrogen can never be the central atom. Again, we have to put oxygen at the center and then put hydrogen at the periphery. Hydrogen takes 2 what? Remember that? It takes 2 lone pairs, right? And what again? Sorry, it takes 2 bonds and forms 2 lone pairs. It already took the 2 bonds. You can't put any other thing here. What do? You're going to use lone pair to satisfy it. So what are you going to do? It has 2, 4. You're going to say 6 and 8. And this becomes the Lewis structure of water. Without having to count. You see, we drew all this molecular structural formula or Lewis structure. This is a Lewis structure. Without having to count the number of bonds. So the Lewis structure means structural formula. But now, we're not going to be using the word Lewis structure anymore. We're going to be using the word structural formula. We now go to the last thing we're going to be talking about in this class. Condensed versus expanded. Now, condensed structural formula is writing the structural formula without showing the bond at all. You don't show the bond. Expanded is where you show all the bonds and show the connectivity. That's what we mean. So expanded means the shortcut or the short form. The short form. This is the full. Expanded means the full form. That's what we mean. The full form. In the expanded, you are showing all the bonds and the atoms. You show all the bonds and the connection. Here you show only the atoms. You don't show the connection at all. Now let's do this quickly. Now look at what happens here. We're going to be doing this more in this class. Whenever I see CH3, I talked about this, I think, in the last problem. Whenever I see CH3, CH3 simply means carbon attached. Okay, wait, that is too close to the. Okay. Means carbon that's attached to hydrogen. This is actually called a methyl group. We're going to talk about this much later. And then, whenever I see CH2, CH2 simply means carbon attached to hydrogen. So knowing that now, we're going to draw the Lewis structure of this. How do we do it? We open this up. So this is going to be C is first of all attached to hydrogens. Then this is attached to 2. Oh, okay. See the mistake I made. I just saw what I did wrong. This is wrong. It's supposed to be this. Oh, I put it was wrong. Okay. Now, so this is CH2 because it only has 2. That's what we mean. CH2 here. So this is CH2. This is CH3. So we have CH2. CH2 means you're going to have only 2 hydrogens here. And then another CH3 here, like this one. You're going to have this. So this is the expanded structure of this is the condensed formula. This is the condensed form. And this is the expanded. Or if you don't want to call it expanded, you can say extended. Because all the bonds are shown here, the bonds are not shown. Let's use this to finish the other problems. Look at this one. If you look at this one again, we'll start with CH3. So C is connected to this. Now, this is connected to oxygen. Look at the way it is drawn. What it means is that this oxygen is also connected to another metal group, another CH3. And then, of course, hydrogen will always have, oxygen will have 2 lone pairs around. Like I said, we're not going to be talking about the lone pairs, but important that I keep showing you this at least in this review lecture, in this review class. Now, let's do this one. This one is easy. Here, carbon has this connected to oxygen. Oxygen is connected to hydrogen. Again, oxygen has 2 bonds. It must have 2 lone pairs. This is the structure of that. This is actually called a methanol. What about this? Now, for this one too, now this one has, remember, don't forget, this is C connected to this, and then this is connected to this. C has CH2 hydrogens, and this is connected to nitrogen. And on this nitrogen, we have what? 2 hydrogens. That's what we showed here. And now, nitrogen, remember, from what we talked about, nitrogen will always have what? 3 bonds around it and 1 lone pair. This is how we draw the Lewis or expanded structural formula of these molecules. Like I said, without having to resort to be counting the number of electrons. That makes it go very fast and easy. Once again, we've come to the end of the lecture. Thank you for listening. Bye.